I'm sorry we started late. Here's what you missed. Just pause this. Force is on a wire. I'm really sorry about this. I did it again. Those of you who are away trying to watch this video. We have a third right-handed rule now. Pause the video. Pick one of these and absorb it. Add it to the back of your formula sheet. And now here we are. Ignore this piece here. This was a conversation we just had with Zach. Okay, example 3. We're going to find the direction of the magnetic field on the wire as shown. Now, this is going to require some remembering. Which way does current flow in this diagram? It goes from big to small. The electrons flow small to big, but the current flows big to small. Because big is the positive side, this is the negative side, so this is the way that current is actually flowing. Electrons are going the other way, but current is going that way. So we've got current, then if we follow the loop, it's traveling down that way. My magnetic field is going which way? No, the magnetic field from these bar magnets. From north to south, you're going to the right. Okay, this is the magnetic field from those, not the wire, but it's the magnetic field from the magnets that are present. So which way then is the force? It doesn't matter which right-handed rule you pick, but you've got to embrace one. If I use the open-handed one, the thumb is the current. The direction of my fingers, I'll just look at my shoulder here, the direction of my fingers are pointing is the direction of the magnetic field. So I can see my palm. So the force on the wire is up out of the page.
Yeah, that makes sense too.
Okay. Conversely, you're using this guy here. The thumb is the current. My middle finger is the direction of the magnetic field. My thumb then is the force if you're using this guy. So that's going to say, oh, I have to bend myself a little bit here. Or I could just, rotate the page. Current's going that way. Magnetic field's going that way. So the force is the direction my thumb is pointing straight up out of the page. Doesn't matter which right-handed rule you use. Pick one, make it your life. So my force then is this way. A dot. The force is out of the page. Here's example 4. More of the same. Applications of right-hand rules. Sorry? Applications of right-hand rules. What's the direction of the force here? Use the right-hand rule. I've heard 3 of the 9 available options.
Oh, wait, no, I have
6 available options, rather. In, out, left, right, up, or down are your options, and I've heard 3 of them. I've heard 4 of them now. Okay, right-hand rule. Here we go. Which right-hand rule do you want to see? How many, just hands up, how many of you are using this right-hand rule? Just so I know who I'm talking to. Is anyone using this right-hand rule? Okay, hands up if you're using this right-hand rule. Abby, yeah, there's hands. AJ? Okay, so then this is the one I'm going to use. Okay? Current is my finger, my pointer finger. My middle finger is magnetic field. So to model this, either I can dislocate my shoulder, or I can just spin the page. Well, either way I have to dislocate my shoulder. I want that. Oh, I need to do this. Oops. I need to do this. My finger is pointing in the direction of my current. It's going from north to south. So that's my middle finger pointing this way. So which way is my thumb pointing? Down into the page. So the direction of the force I've got here in green, that's my force into the page. because I need to orient it properly. This is backwards. I guess I didn't need to turn the page. My pointer finger in the direction of the current. I could just do this. My magnetic field's going to the right, so I have to spin my hand over to make my magnetic field go to the right. My thumb down into the page is the direction of the force.
Your magnetic field, you can go from north to south.
Is that because the B value is
So
going
it can't be like this. You gotta.
That's because B is going north to south. Yeah. So now I've got B field going this way. So my middle finger has to point along that direction. Oh boy. My current's going up. In the next example, it's going up out of the page. Like out of the page. It's like this.
But isn't our current going up as well?
No, current's coming out of the page.
Out of the page.
Up out of the page. My magnetic field is going up the page. My force is going left.
I know, but how are we supposed to up?
No. This is up. This is that way. Thumb is that way, to the left. Yeah, like that. Now tilt it up. Now tilt it towards you. Because that's the direction of the current. Your finger's pointing in the direction of the current now, Joseph.
Yeah.
So the magnetic field is... No, and spin it. No, other way, because the magnetic field's going that away from you. Spin it the other way. Now point your middle finger out.
Out.
Yeah, so that way. That's the setup, Joseph.
Okay, so this
Current.
Yeah.
If it helps you for today, write them on your fingers. This is current. This is magnetic field. This is force. Write it down if you have to. AJ's already done it. I, B, F. Write it down. I will not check your hands prior to your test on this. I will not be checking your hands prior to your test on this. Just toss that out there. Okay, next one. Magnetic field's going this way. There's my B. Oh, wait. We have to actually write the answer down. Force is going this way. F. My B's going that way. Current's going into the page. Direction of my force is? All of you, right-hand rule this thing. I want to see all of you dislocating yourself. When you do AJ, that doesn't mean anything to me. Does that mean it's down into the page? Does it mean it's down the page? Like, because now we're in 3 dimensions. The words are important. AJ says it's down the page. I also agree with AJ. Okay, next one. This guy here. This one is going up the page. Good job, Zach. Verify that for yourself. That is true. Make sure you understand it.
True, you're right, yeah.
Okay. Look at the next one. My current is going in the same direction as my magnetic field. No, that's not how this works. The right-hand rule has to look like this. You cannot warp the right-hand rule to say, oh, it's just this. That's not how this works. If the right-hand rule doesn't work, no part of the right-hand rule can work. So, because my current and my B field are in the same direction, there is no force. If the right-hand rule breaks, there's no force on the wire.
Then would it be the same for the other one? The current is the same. The current, magnetic field.
This is an interesting one.
Right here.
What's going on there? It's on an angle. So is it totally parallel? No. Is it totally perpendicular? No. But it's a little bit perpendicular. There is a component of it that's perpendicular, and there's a component of it that's parallel. So I've got my current moving that way. and my current's moving this way. I've got I parallel and I've got I perpendicular to my magnetic field. So that's not going to say this there was none, this there was a max. So this guy, the force is going to be somewhere between here and here. There's a relationship that exists that involves what happens at weird angles. Just like torque had a relationship between angles, this one does now as well. So we have to look at the fact that there is a part of the wire that is moving perpendicular to my magnetic field. So we're still going to have my current going that way, my B field going that way, my force into the page. There is a piece of current going that way, a magnetic field going to the right, my thumb's down into the page, and then so my force is as well. Ursula, you got to be careful not to draw. It's not men. Got to be perpendicular.
Why?
Because there is a piece of the. Sorry, Joseph, answer.
Yeah, we're doing because it's a vertical and there's horizontal component of the current. So the horizontal component can't like because it's in the same direction as the magnetic field. There's no force. The purpose or the vertical component is going off. So let's go in the direction of the current. That's this finger, right? Yeah. And now if we want our magnetic field going out, we flip it, and now something else. The force.
Everything Joseph said was correct.
Let's go to
Yes.
So if you can wrap your head around what he explained, that's correct. What about this guy here? I got a wire passing through the center of the coil. What's going to happen to this guy? Which way is my B field going? We're using multiple right-hand rules now. My B field, the current's going this way, so my wire's going, or the force, sorry, no, all the things are wrong. My magnetic field is going to the left. I've got a hanging wire. You can picture it like you'd slide a wire in the middle, like between a slinky. So it's hanging there in the middle of the coil. So I've got a current going that way. I got my force going that way. Sorry, my magnetic field going that way, so my force is going up out of the page. This guy, what's going to happen here? No, what? Careful. Currents to the right. Magnetic field is which way? There'd be parallel, there's no force. Good.
So when they're parallel, they cancel each other out.
There's no way to.
There's no canceling, there just isn't any. Like the magnetic field doesn't cease to exist. There just is no force.
So there's no way to orientate your fingers.
No, he's asking why it happens physically.
Oh, no.
That's an easy way for you to remember it, but that's not why the universe is the way it is. Well, I can't move my fingers, therefore the universe is broken. No, that's an easy way to remember it, Nathan. That's not why it is. Okay. Here we go. So, I'm not going to get you to derive this. Experimentally, we have verified that this is the relationship between the force, the wire, the magnetic field, and the current. It's given to us by this expression here. F on a wire is given to us by lib. And we're going to add some subscripts here. We're going to make it I perpendicular. And the pieces of the current that are perpendicular to the thing. We've got the B. B is the B external. Not the B field from the wire itself, but an external pre-existing electric field. Magnetic field, sorry. And L is the length of the wire that is present within the field. The more wire that's in the field, the larger the force, which should make sense. No, the length of the straight wire located within the external magnetic field. So in this case here, looking at this example, this length right here is the length of the wire located in the magnetic field. That's the length we're going to use. Not how long the wire is totally, just the piece that's in the magnetic field. Because the rest of the wire doesn't experience a force. It just gets dragged along for the ride. And, as always, because this is a vector, we need direction. The direction is found using the right-hand rule. That's an RHR. It looks kind of gross, but that's what I wrote there. So, here we go. We're going to find the magnetic force on the wire shown if the magnet produces a field of 5.4 milliteslas, milli being 10 to the negative 3. So, we need the current in the wire. We're not given the current in the wire, we're given a circuit. I don't get to teach you circuits this year, so you got to remember, and I gave you, it's on the formula sheet, I equals V over R. My voltage is 6 volts. My resistance is 2 ohms. So my current is what? 30 amps. That is a huge current. 4 amps can kill you. So yeah, this could kill you a few times over. If you put half an amp in the right spot, it can kill you. So. Okay, so the force from the magnetic field on the wire is going to be equal to the length of the wire, the amount of the current, and the strength of that magnetic field. So the length of the wire is what? In meters. 0.22 meters. The amount of current we already established is 30 amps. The strength of the magnetic field is 5.4 times 10 to the negative 3. So what is the magnetic force on the wire? You did that incorrectly. Round it to 3 decimal places. 0.036 newtons, and the direction is which way? Let's go back to our diagram. Draw in the B field. The current goes around from the large line to the small line, positive voltage to negative. So this is the direction of my current. That's I. Use the right-hand rule. What's the direction of the force? Current is pointer finger. Magnetic field's going that way. There's my thumb. Force is out of the page.
Boom, boom, boom. North to south, right? Yeah. Magnetic field's got to go that way.
Oh, shoot dang. I put the thing in the wrong spot. Shoot dang. Scribble out this one. That perpendicular thing. It's easier to look at components not on the current. You could. That's harder to do. So I apologize. We're going to put it right here. We're going to look at the components of the magnetic field that are perpendicular. Conceptually different, mathematically equivalent. I apologize for screwing that up. Yeah, these are physics gang signs. I taught you 3 of them. We're not going to do the exact, we're done with page 516 because I've shown you those already. If the current and magnetic field are parallel to each other, there is no force. And I've given you, so let's go to the formula sheet here. We're going to add something here. Go down to this guy here, F equals lib. The thing we're going to add to this is that the lib is external, ext, comma, perpendicular. For the easy questions, they'll set them up perpendicular for you. For the harder questions, it'll be off at an angle, and you're going to have to calculate what portion of it is perpendicular using sine or cosine or whatever the setup of the problem is. So here you go. Here's what I want you to play with. Gersa Hill, what am I going to assign? Take a look at the questions. Zach's got his guess too. Oh, I'm frozen. Oh, look at that. I'm frozen. We're not doing 9, because 9 is old stuff. Here's what I'm going to assign onto you. 1, 2, 4, comma. Page 517. 6 to 8.
1, 2, 4.
1, 2, 4, not 1, 2, and 4. 1 dash 4, and then comma 6 dash 8. That is your homework. You have lots of time to work on this. I am not going to do the next lesson today, but we are going to finish magnetism tomorrow. And I will have the reviews for electrostatics and magnetism for you guys to pick up tomorrow, because I had interviews yesterday. I couldn't get them done, Shannon. Sorry.
There's a pretty interesting demo. It's just physics and math in general, but electro.
Oh, sorry, 1 second. No, it's good. I like 7. Yeah, 7's good. Sorry? Yeah, go for it. Yeah, absolutely. There it is.